Hello everyone, this is Mr. Sorrentino again, bringing you another one of these lecture videos, and this one is for Math 31, dealing with section 2.4 and 2.5, which deal with symmetry for 2.4 and transformations for 2.5. So there's three types of symmetry that they want you to focus your attention on, and make sure you know the difference between a graph having some sort of symmetry, which means graphs can have symmetry. Basically, if you can imagine, a line being put through it where it cuts it exactly in half in some way or something of that nature. But it doesn't necessarily have to have these types of symmetry. And it's these types of symmetry that we're mostly focusing our attention on for the point of 2.4. You have symmetry about the x-axis, and they give you a test for that. If replacing y with negative y produces an equivalent equation, then the graph is symmetric with respect to the x-axis. As far as what the graph would look like, some graphs that would look like that would look an awful lot like this. Where you can see that, something on this side here, something like up here, has a mirror image on the other side of the graph, and same thing here. If I look at these, it has a mirror image on the other side of the x-axis. We don't really focus too much attention on symmetry about the x-axis because symmetry about the x-axis is an indicator that you're not going to have a function, because if you look here, I mean, clearly both of these fail the vertical line test miserably. I mean, if I put a vertical line here, here's two spots where this graph passes. I put a vertical line here. Heck, I have 1, 2, 3, 4, 5, 6 spots where it passes through. So these symmetry about the x-axis is going to be typical of something that is not going to be a function. So we really don't focus too much attention on that particular kind of instance. The next type of symmetry is symmetry around the y-axis. And they give you a test up there, which we are going to make use of as we go through this. But y-axis, if replacing x and with negative x produces an equivalent equation, then the graph is symmetric with respect to the y-axis. So, case in point, some examples of being symmetric about the y-axis are these two graphs. So now, I can see that same kind of relationship of me having a point on one side of the graph, like say this point here, I'm going to have a mirror image of it on the other side, and that's true for any point. Same thing over here. I have this point down here, I have a mirror image of it on the other side of the y-axis. This is typical of functions. I mean, so there are a number of functions that do have symmetry about the y-axis. So it is something you're going to see from time to time. Symmetry about the origin is, easier explained if you look at it, but basically the test for that is if I replace x with negative x and y with negative y, I get the exact same equation again. Or, there's different ways of testing for that, and I'll show another test for that as we go through this. However, some examples of that are here in this image. And I can have, symmetry about the origin and have functions like these two written in red. Those are functions, and the one in blue has symmetry about the origin, but it's not a function. And essentially, the way that works is, you can tell you have symmetry about the origin if it looks as though, if I pick a random point, so for the sake of argument, say on this graph over here, I'm looking at the maximum here. If I can imagine me like doing a mirror image of it over here, over the y-axis, and then doing the mirror image of that over the x-axis. So it's kind of like, whenever you're more or less, moving things about axes, you're moving them about both axes. And that's what's going on with this. So as I said, these could be true with functions or non-functions. And the last type of symmetry, well, not the last type of symmetry. I mean, here's this. I mean, there are some that have all these symmetries. Like for instance, a circle. It's symmetric about the origin. It's symmetric about the x-axis. It's symmetric about the y-axis. Once it becomes symmetric about the x-axis, you're going to lose the ability to have any type of, it's not a function. This fails the vertical line test. And then of course, you have examples that have none of these symmetries. Now each one of these figures are basically figures that I've shown previously. However, they've just been moved a bit, so they're no longer symmetric about a particular axis. So like for instance, up at the left hand corner, that's a parabola. Here's the y-axis right here. I don't have an exact mirror image of anything on the left, on the right. So I have a point here. Its mirror image would be here, but the graph doesn't pass through that. So the graph has some sort of symmetry. The symmetry would not be around the y-axis anymore. It'd probably be on the line x equals 1. But those are things that we talk about when we get into transformations. It doesn't have symmetry about the x-axis either. It doesn't have symmetry about the origin. So, all of these are examples of, functions up here and non-functions down here that have neither symmetry. So recognizing it in the graph is important, but we're going to often do algebraic tests to determine that as well, but we're going to add another parameter to it. So let's have a look at that. And those parameters that I was talking about are centered around even functions, odd functions, and functions that are neither. So an even function, the test is essentially if f of negative x equals f of x for all values of x, then it's an even function. Or if I look at a graph, it's symmetric about the y-axis. So symmetry about the y-axis makes it an even function. And the important thing to note is we are talking about here functions. Everything we're talking about deals with a function. So it has to be a function. It has to pass the vertical line test, so forth and so on. Now, there's also here mentioned a shortcut for identifying them. Even functions typically have even powers of x or absolute values of x only. So, there's no like, quantities being raised to powers. And all the powers are going to be even numbered powers, or might have an absolute value around it. That's it. That's a good way of identifying which way you think it should go. It is not, however, a determination. Okay, so if you're asked to determine if it's even, odd, or neither, you can't just state this rule and say, okay, that's enough. That's a way of saying, well, I'm expecting it to be even. Let's see if I can prove that it's even. So there's a difference between, expecting it to be even and then actually proving it. The other type of function, of course, is an odd function. I have an odd function if I replace negative x in f of x, and I end up with the same thing as if I took f of x and multiplied it by -1. It's a little bit more involved test, involves a lot of distributive property, but we'll show what that means. Essentially what that means is that the graph is symmetric about the line y equals x. It's also known as being symmetric about the origin. So, symmetry about the line y equals x and being about the origin mean the same thing. So, symmetric about the origin, symmetric about the line y equals x, same thing. The shortcut, again, is that odd functions typically have odd powers of x only. So not quantities of x, but just x's, and each of the exponents, as you can see, like here, 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 and here, there's a 1 over here. So that's technically the same thing. They're all odd numbers. Again, that helps me determine or get an idea of what kind of function it is. It is not proving it to be the same thing or determining that it is. And also keep in mind that we are talking about that these are indeed functions. So you're not going to see any type of function as a result of being symmetric about the x-axis, because as we mentioned before, that's not a function. It fails the vertical line test if it's symmetric about the x-axis. So basically these types of symmetry lets me define whether it's an even function, an odd function, or neither. So neither just means, well, it's not even, it's not odd. So it doesn't have any type of symmetry about the y-axis, or it doesn't have symmetry about the origin. So let's have a look at example 1 now. There's two types of problems you can be given where you're asked to determine if functions are even, odd, or neither. They could be graphical, which are pretty straightforward. You just have to kind of look to see, be able to recognize the types of symmetry. Or there's algebraic. Those involve a little bit more work and you have to be more definitive. You're going to be asked more often for the algebraic one. So A, B, and C, although easy, and you may be asked a question here or there about it, they're going to be less likely because they are pretty straightforward. You can kind of recognize it on sight. Here, the axes are kind of hard to see. So there's the axis, and I can see, if I look at this point down here, I can imagine me like doing a mirror image of it over here, and then a mirror image of that over here, and that's pretty much true for all the points. This is showing symmetry about the origin. And with symmetry about the origin, it's an odd function. So it's an odd function because it has symmetry about the origin. On the next one over, again, here's my axis to kind of, if I pick this point down here, I do a mirror image of it, I don't have anything over here, between -2 and 3, or 2 and 3. So I know it's not symmetric about the y-axis. And if I were to flip this up here and do a second one, which should be up here about, about here, I would expect the point to be here for that mirror image if it was an odd function. So this doesn't have any of the types of symmetry that we're talking about. So this is neither. And again, for the sake of emphasis, I can see the x-axis okay. The y-axis, let me make sure it's. I can see that if I pick like a point right here, its mirror image is also on the graph on the other side of the y-axis. So this does have symmetry about the y-axis. And it being symmetric about the y-axis, it's going to be an even function. So graphically, once you get the hang of understanding what they look like, as far as being symmetric about the y-axis, being symmetric about the origin, even being symmetric about the x-axis, so you're aware of what that is, and you can even say in those cases it's not a function. When you look at symmetry about an odd function, it's kind of like being symmetric about both axes at the same time. So you kind of need to know that idea of the x-axis symmetry as well. But you get the hang of it, you can kind of recognize them pretty quickly once you get the hang of seeing them. Now, on the other hand, algebraically, they do entail a little bit more work. So let's look at the next three parts of this example. So in D, and you're told to show algebraically, but anytime you're given a function and it's a formula and you're asked to determine if it's even, odd, or neither, you do need to show some algebra that, backs up what you say. So for this one here, for anything to the 0 power is 1. We talk more about exponential rules as we move through this, but this is an exponential rule that's taught in a lot of pre-algebra courses, so it is one that you're expected to kind of know when you're in this one. And also, along with that, 0 is an even number. So I would expect this to be even. Now, that's not, by any stretch of the imagination, a proof that this is even. So what I need to do for this is, first I need to keep in mind what f of x looks like. And then I want to evaluate what f of negative x is. And if you remember, that just means going everywhere I see an x in the original formula. Now, I'm not going to write it in this format because it's just extra work to do. I'm just going to leave it in the other format. It's just important to notice that if you have a constant in a function, that's like having an x to the 0 power, which means that's still potential to be even. And so when I do that, I'm going to have 2 times negative x squared, the quantity of negative x squared, plus 5. Well, if I square a negative value of anything, it's going to become positive when I square it. So this is going to be 2 positive x squared plus 5, which is the exact same thing as f of x. So as a result, by the test we defined above there, since f of negative x equals f of x, this is an even function. So beforehand, I had kind of determined that it was based off of the shortcut, but this is the work that needs to be shown to justify me saying it's an even function. Let's look at part E. Now, as I look at part E, this f of x, I can think of this as being x squared plus 2x to the first power. I have an even exponent and I have an odd exponent. So by the shortcut that we defined, since it's not only evens and it's not only odd powers I have here, I would expect this to be neither. Okay, but again, that is not any kind of definitive proof. So what I need to do is first acknowledge what f of x is. I'm going to do f of negative x, which means I'm going to go to this function up here and replace all the x's with negative x's. So I'm going to have negative x squared plus 2 times negative x. When I simplify that, squaring a negative x is just going to make it a positive again, so there's no more negative needed. But a multiplication of a positive 2 times a negative x is going to give me a minus 2x. So f of x was originally x squared plus 2x. F of negative x is x squared minus 2x. So I could say at this point, this doesn't equal f of x. So I can say at this point it's not even. In a very similar notion, I could do negative f of x. And we're going to get more into this noticing of what goes on inside parentheses versus what's going on outside parentheses. If I'm doing the opposite of f of x, I'm doing the opposite of this entire quantity. Which is like having a negative 1 times that entire quantity. And when I do that, I get negative x squared minus 2x. Well, with this piece of information and seeing this up here, I can make the conclusion that, well, f of negative x doesn't equal negative f of x, which is the condition needed to be odd. So I could say, well, based on that, it's not odd either. So as a result of that, f of x in part E here is neither even or odd. And lastly, let's look at part F. Now in part F, when I look at this again, I can still imagine there being a 1 here. That means that both of those exponents are odd. And since all of the exponents involved in this problem are odd, I would expect this function to be odd as a result. Again, that's not a proof, so I shouldn't just make a statement like that and say that's my proof. I need to go through the tests. So again, I'm going to do, okay, with that being f of x, f of negative x is going to be negative x to the third power plus 2 times negative x. When I simplify that, negative x times negative x times negative x, well, negative x times negative x is x squared. X squared times negative x is going to give me a negative x cubed. And of course, a positive 2 times a negative x is going to give me a minus 2x. So I can say for certain that this does not equal the original f of x. And I can conclude as a result this is not even. So now I have to go and figure out what negative f of x is. Which means I'm taking the function f of x and multiplying it by negative 1. So I'm going to have negative 1 times what f of x is. That's x cubed plus 2x. When I distribute that negative 1, I get negative x cubed. A negative 1 times a positive 2x gives me a minus 2x. And as I can see now, based off of what I see up here, this equals f of negative x from what I determined above. And because of that, this is an odd function. And so those are the algebra tests that you have to show when you're being asked about even, odd, or neither. And make sure that you do run those tests, because if you don't, then you could be right in the conclusion, but the work involved is not being shown outright as you should be. And that's basically what symmetry is. That's what you have to do for the symmetry unit. That's why it wasn't really worth the time to like just split it up from the other part. This next part's a little bit more involved, so let's get into it. We're going to move into graph transformations now, and as a warning, and I have this in your notes as well, I do teach the methodology of doing this a little differently than a lot of TAs might have learned how to do it, and actually it's a little bit different than how the book presents it. The book will have you do, especially when you get to multiple transformations, it'll have you do it using a method where you're doing one transformation at a time. So if you have like multiple transformations, you have to do each one individually and keep track of where you are, and that can be kind of tough. Whereas mine's a little bit more direct as long as you know what it is you have to do. So when we get into graph transformations, the whole premise behind it is that, if you look at any particular graph that you're given, they're going to be related, like the functions we're looking at, primarily at this point, to any one of these functions, where I have, f of x equals x, which is just a line, f of x equals x squared, which is just a basic parabola, f of x equals x cubed, f of x equals the absolute value of x, f of x equals the square root of x. And these will be basically where you're going to be making your graphs from. You're going to start with these basic functions. And these are all functions. I mean, technically, just existing, just having an x exist makes it a function. Squaring is its own special function. Cubing is its own special function. Absolute valuing is its own special function. Taking a square root is its own special function. I can apply this to cube roots. We'll eventually apply techniques like this to exponential functions. We'll apply this to logarithmic functions as we move through this course and do some other things with them. And it's important to note that because, essentially, these parent functions, and the reason why they're parent functions is any of the interesting graph behavior, if there really is any, tends to occur at the origin. If you look here, there's the line, not really. I mean, the line just passes through the origin. For the parabola, that's where it reaches its bottom point and then goes up and then starts going up in the other direction. At the origin for x cubed is where it has that flattening you see going on, and then it moves on from there. For the absolute value function, that's where that corner point is. For the square root of x, that's where the graph actually starts. I mean, so there's always something unique and interesting happening at the origin for these parent functions. But functions related to these are not necessarily going to have that interesting thing going on at the origin. It may be located in another coordinate. And the problem with doing the graphing that we had been doing before, except for the line stuff, you're not going to see us do many transformations with lines because we have methods of graphing lines that are a little bit more specific. We have slope-intercept form, we have point-slope form, which both are related to concepts that this graph transformation stuff occurring kind of relates to. But if I go back and graph more complicated things the way we had been at this point, just picking some random x's and then putting them into the function, get y values and plot them, you run into a difficulty because sometimes, students will always go like, usually it's like, I'll pick 1, 2, 3, 4, 5, 6. And they'll put those in, but maybe all the interesting stuff isn't happening there. Maybe it does reach a maximum point or a minimum point somewhere else at a point you're not choosing, at an x value you're not choosing. And so you end up missing some of the behavior. I've had students who have told me that, something with a square in it looks like a straight line. Well, it doesn't. It should look like a parabola. And that's only because of the fact that they say that because they just put 1, 2, 3, 4 in. Meanwhile, all the interesting stuff, the turning around of the graph happened when x equaled -7. And they didn't try that number, and as a result of just not putting that particular number in, they don't see what goes on with the function. So these techniques or having you stem these from a parent function where the interesting happening occurs at x being 0, and therefore we transform that as well as everything else according to some transformation rules that we're going to introduce as we move through this. So there's several different types of transformations that we're going to talk about. The first one deals with translations, which are also known as shifts. These are going to be things that cause the graph to move in one direction or another. Okay. So, the first type we have is a horizontal translation. These occur when I have numbers inside of the parentheses on my function. So you notice here that I have a -2 in here. I have a +3 in here. Translations and anything that deals with horizontal transformations, you have to pay particular attention to. Horizontal transformations work a little, differently than vertical ones. Notice here, it's telling you that for a value of d greater than 0, if I have f of x minus d, then it's causing it to shift right d units. Meanwhile, we're used to subtraction meaning moving left. This is saying that if I have a subtraction inside the parentheses, I'm actually moving right. So as a result of that, basically when I look at these two functions up here, I have my original function, my parent function for this, and I'm going to put it up here. It's kind of small. The parent function is usually going to be the exponent or a special function. So the parent function is f of x equals x cubed. And as you can see, that's what's graphed here. That's why you can see here I have the 0, 0, I have the 1, 1, I have 2, 8. So I have these points I'm looking at here. And the parent functions, you're going to be expected to know how to produce a table with the values, enough values for it to be somewhat reasonable really quick. So -1, -1, -2, -8, 1, 1, and 2, 8. That's the parent function. For each one of these, I'm going to alter the parent function. So when I see x minus 2 cubed, so I know it's related to a cubic function. And this is telling me for the x's, I'm going to add 2 to the x coordinates. So that means when I do my table for the graph for this, I'm going to have an x and y chart. The y's are going to be left alone from the original function I have up here. Each of the x's are going to be added by 2. Whereas when I look at the next one, I see x plus 3. This is telling me to take my x coordinates and subtract 3. And so when I do its table, again, since these are horizontal transformations, it does not affect the y's at all. So I'm going to have the exact same y coordinates. The x's are going to be subtracted by 3. So the horizontal transformations, at least so far for translations, I'm doing the exact opposite of what I see in the parentheses. If it says subtract 2, I'm going to add 2 to the x coordinates. If it says add 3, I'm going to subtract 3. When I look at the vertical transformations, now notice the vertical transformations, they occur outside of parentheses. So notice it's not the x being subtracted by 2, it's the x cubed being subtracted by 2. So I'm still starting with the same function, except now I'm going to have the -2 applied to the y's, not the x's. Here I'm going to have the +3 applied to the y's, not the x's. So when I look at this next graph, I'll do this one in this one here, the x's are what's going to be left alone because anything occurring outside the parentheses is indicating a vertical transformation. So that's the first thing, is that the vertical transformations occur outside the parenthesis. Horizontal ones occur inside the parenthesis. And this is telling me now that I need to subtract 2 from the y's. And notice here, a plus b means shift it up, Well, that's what we expect because on the y-axis, when I add numbers, I am moving up. When I subtract numbers, I'm moving down. So it seems as though when I was doing the opposite for the x transformations, the horizontal transformations, I'm going to do exactly what I'm told to do for the y's. And these are the points I am going to plot now. Whereas for this one here, again, that plus 3 is occurring outside a parenthesis. And if I don't see a parenthesis in the formula, I can just assume that it's occurring outside the parenthesis. It's a vertical transformation, so I know that none of the x's from my original table, this one right here, are going to remain unchanged. And I'm always going back to that parent function table. And now each of the y's is going to be added by 3. So these are the points I would have, with this vertical transformation, and I'm going to plot them. Much like we did with the circle graph we talked about earlier in this, I'm not looking for perfection on this. I would like to see the emphasis of points being shown, and you should certainly show the table of values that you use to plot your graph when you do these various transformations. So that takes care of shifts or translation. Let's move on to the next type of transformation. The next type, it kind of gets into the same kind of rule that we have to worry about when we deal with the next type of transformation, but we're going to look at reflections. And reflections are basically, I'm going to reflect something about an axis. Now notice in this example 3, I have the square root symbol in there. So that means that my parent, y equals, or f of x equals the square root of x. And again, you should get yourself to a point of being able to produce the table really quickly. Now, x's can't be negative for this function. It's the only one that has a domain restriction. 0, 1, 4, 9. I'll even go up to 16. I'm picking perfect squares, so when I square root them, I'm going to have 0, 1, 2, 3, and 4. So again, I should be able to know how the function works well enough to produce a decent parent function and, get something to start with. And if I plot all these points, I mean, here's 0, 0. I guess I have to guess where 1, 1 is. It'd be about here. 4, 2 would be about here. 9, 3 would be here. 16, 4 would be here. So you kind of get the idea of where these things need to be. What I have for part A is I have a negative in front of the square root symbol. The square root symbol also acts as a grouping symbol. So basically, and that's why if you notice if you put on your calculator, when you put a square root symbol in, it comes up with square root, and there's oftentimes a parenthesis with it. It's a grouping symbol too. I could take the square root of a whole expression if I wanted to. Since the square root symbol is a grouping symbol, technically that negative is happening outside of a parenthesis, which means this is a vertical transformation. And as you can see here, if I have y equals negative f of x, it reflects across the x-axis, which means it's changing the y coordinates. That means that this is a vertical transformation, which means all the x's I had before, 0, 1, 4, 9, and 16, they're going to remain untouched. The y's are going to change. And this says I'm going to multiply by negative 1. Well, multiplying by negative 1 is just going to make these 0, negative 1, negative 2, negative 3, and negative 4. And so when I plot those, basically making all these mirror images. And again, I'm not looking for perfection on this, so long as you have some of the points emphasized, and you have this thing down here, it lets me know what you did. So much like the transformations I did for vertical translations, for the vertical reflection, did what I said. A negative symbol means multiply by negative 1. I took my y's and multiplied by negative 1. As I explain what goes on for part B, because a lot of people think that somehow there's a different thing going on for part B, it isn't. There's a trend with how these things work with each other. So in part B, you notice that the negative occurs under the square root sign, which means it's occurring within the parentheses, within the group defined by the square root symbol. So that means that, I have something that's going to affect my x's. My x's are going to be affected here. It's a horizontal transformation. So when I start my table down here, the original y coordinates from the parent function are going to be held there. So 0, 1, 2, 3, and 4 is still going to be the case. Now here's what you have to realize. This -1 inside there, what it's doing is multiplying by -1. I always do for just like for the transformations I've done beforehand with the horizontal translations, I'm going to do the opposite operation. Notice I said operation, not the opposite number, opposite operation. So when I was adding, inside the parenthesis, that would indicate to me to subtract. When it told me to subtract, it told me that I needed to add. Well, here, since I'm being told to multiply by -1, and multiply is the operation, I'm going to do the opposite. I'm going to divide by -1. I'm not changing the sign of the number. I'm changing the operation. Now, it just so happens multiplying by -1 and dividing by -1 does the same thing. If I multiply by -1, I change all the signs. If I divide by -1, same thing. And it's only because of the fact that 1 and -1 both have themselves as reciprocals. And the end result is I'm going to divide each one of these by -1, but as a result, I'm going to have different signs on the negative of the 1, the 4, the 9, and the 16. And so what that ends up looking like, it's the opposite operation that's being done here, which will make more sense when we get into stretching and shrinking, because it's the same operation. It's multiplying occurring either inside or outside the parentheses. So let's look into this. Stretching and shrinking. You see, I have a couple examples here, but let's focus on these rules first. A vertical stretch and shrinking. Notice that the multiplication is occurring outside of the parentheses, whereas for horizontal, it's occurring inside. They define what stretching vertically and stretching or shrinking vertically is. You'll see what happens when that happens. But essentially, the reason why what goes on with this and what this is actually explaining is, if I have it occur outside the parentheses, like these two, here the absolute value is the parenthesis, the squaring is technically the parenthesis. You can see it more so here. Outside the parenthesis, it's vertical, which means I'm going to do exactly what it tells me to do, whereas it's inside the parenthesis, it's horizontal. I'm going to do the opposite of what it tells me to do. So for these two, the parent function is y equals x squared. In my table for that, you go a little further with it if you want. You can go as far as you want with it, as long as you can produce x and y values rather quickly. It doesn't matter. This is telling me that, okay, this is outside the parentheses, so it's affecting the y's only. And I'm going to multiply my y's. So all my y's are going to get multiplied by 2. So the table for this, all my x's will be left alone. Each of the y's is going to get multiplied by 2. So when I graph these, now notice, I mean, this is considered a vertical stretch. A lot of times a vertical stretch will look like a horizontal shrink. Sometimes they are the same thing, sometimes they're not. But I know it's a vertical stretch because of the fact that, things are moving up away from the original graph, and it's a vertical, transformation. Whereas this next one, I'm still starting with the same parent function. This is telling me that, well, it's occurring inside a parenthesis, so it's a horizontal transformation. So it's going to affect the x's only. And this is showing a multiplication of 2. This tells me that my x's are going to be divided by 2. It's always the opposite operation inside the parentheses. So that means that when I do my table for this, it's my y's that are going to be left alone from the original function. So the 4, 1, 0, 1, and 4 I have from the original parent function are still going to be there. Each of the x's are going to be divided by 2. Plot these, my graph will look something like that. Now again, notice that it looks like it's a very similar transformation of what I had previously in part A, but it's not. This is a horizontal shrink, not a vertical stretch. They look very similar, but they're different things. And they're done differently because this one affected the x's, this one over here affected the y's. So I have to pay attention to what those are, especially when I start getting into situations where I have multiple transformations, which we'll get to momentarily. Let's look at part C. This one's occurring outside the absolute value sign. Now, absolute values, as you can see here, are the main thing going on here. So my parent function is y equals the absolute value of x. And again, I'm just going to come up with a really quick function for this. So I'm going to have, -2, -1, 0, 1, and 2. And the absolute value is just going to change the negatives to positives, leave the positives and zeros alone. So I have that. Now here I have a 1/5 occurring outside of the absolute value mark. Since it's occurring outside of the parenthesis there, it's going to be a vertical transformation, which means it's going to affect the y's only. This is saying multiply by 1/5, and therefore, since it's a vertical transformation, I'm going to take my y's and I'm going to multiply by 1/5. I do exactly what it tells me to do. So when I start making my function down here, my x's remain unchanged, and each one of these gets divided by, or multiplied by 1/5, or divided by 5. So this is going to be 0.4, this is going to be 0.2, 0, 0.2, 0.4. If I had gone to -5 and 5, those would have a y coordinate of 1. So basically, and I'm going to use that fact to help me out a little bit here. At 5, this would be at 1. At -5, this would be at 1. It makes it a little easier to draw it. So take it as far as you think you might need to draw it. Now this looks like it got stretched horizontally, but actually what happened, and we could tell this because it was a vertical transformation, it got shrunk vertically. That's what happens with this. For this one here, the 1/5 is occurring inside the parenthesis. Horizontal transformation. And it's going to affect my x coordinates. The operation I'm seeing here is a multiplication of 1/5. So this is telling me I should be dividing the x's by 1/5, which, by the way, is the same thing as multiplying by 5. So when I do my table, going back to the parent function, my y's are going to be left alone. Each of the x's are going to be multiplied by 5. So that's going to be -10. That's going to be -5, 0, 5, and 10. And I plot those points. And there you have those points. So again, it looks like, this looks like the same thing happened as what happened in C, but again, horizontal stretches will look a lot like vertical shrinks and vice versa. And that's how you tell the difference between your various transformations. So let's summarize a little bit before we move on to some multiple transformations. So graph transformations rules. Vertical transformations affected by the affect the y coordinates. So if I know it's a vertical transformation, I'm only going to alter the y coordinates. They're identified by operations, addition, subtraction, multiplication, that are located outside the grouping symbol. So it might be a parenthesis whether it had to be put in or not. It could be a square root symbol, an absolute value symbol, cube root symbol even, if we get into those. Eventually logarithms, exponentials, so I perform the exact same operations shown. And the new thing to focus our attention on, this gets more into the multiple transformations. In the instance where multiple vertical transformations are needed, I perform the operations as dictated by the order of operations. That's going to become important. So the vertical transformations are, most students have the least problem with those because they behave pretty much as they look. You just have to make sure that you're identifying vertical transformations based off of things that are occurring outside of a parenthesis. Horizontal transformations, on the other hand, these are the ones that act a little bit bizarre. Now, some of these are expected. They affect the x-coordinates. I would expect that. They're occurring inside the parenthesis. So I'm going to see these additions, subtractions, multiplications, and divisions inside the parenthesis. Now notice these transformations are operations. They're not going to be squares. They're not going to be square roots. That is part of the parent function. When I eventually get to other functions like exponentials and logarithms, those are part of the parent function. So now the big one is that I perform the opposite operation. Very important. So if I see inside of a parenthesis an addition of 3, that tells me I should subtract 3. If I see inside the parenthesis a division of 5, that means I should multiply by 5. And last but not least, the very, 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 very important part of this, in multiple transformations, and this should say horizontal, I would perform the operations, and these are the operations that I now interpret I have to do. So if I see an addition, I'm going to subtract. I see a multiplication, I'm going to divide, whatever the case is. But I also reverse the order of operations, which means, additions and subtractions get done first, then multiplications and divisions get done second. So you want to keep that in mind as well when you do your horizontal transformations. So let's see this at work. Now, another way as we do these multiple transformations, another way for them to possibly show this to you is they could define a new parent function. So like for instance here we have a function. It's not given any specific formula. It's just said, okay, well here's this function, y equals f of x. We want to be able to graph these two functions we see in A and B, which we can see are related to f. So they're basically saying they're related to this, which means I should still see some of the same features. I should still see a sharp corner point. I should see a rounded end to it. It should be a continuous function, no breaks. All that stuff should be in there. So when I follow these techniques, I'm going to need to make sure that as I follow these, that I have a parent function to work from. So I'm going to do a chart for my parent function first. So the parent function, which is the y equals f of x, is going to have some points where, and usually if you're presented this, I'm going to use the ones that have the big dots in them. That makes it a little easier. So it looks like I have -10, 0, -4, -5. I can put any axes in there too if I want to, but I'm not going to. It looks like I have 2, 1. I have 6, 5. And this thing comes to an end at 8, 4. I might also want to keep in mind, like the first 3 points, is the, straight with sharp corner. And, the third through the last ones is going to be the rounded part. This helps me when I eventually have to graph, the offspring. So now I'm going to come down with this as my parent function, and I'm going to now look at graphing y equals -2 times f of x plus 3 minus 1. Now, let me shut this down just ever so slightly. I still want to be able to see the parent function. When I look at this, I'm going to have to, before I do anything on the graph, now here's where the biggest difference occurs between what I do and what your a TA or someone at the Mac may show you to do. They would have you do each one of these transformations individually. I mean, and I can see the transformations are in here. I mean, I have a multiplication of 2 on the outside, which means I would have a vertical stretch, but it's also being a negative 2, which means I would expect a vertical reflection, which means across the x-axis. I see a minus 1 on the outside, which means I would also expect a vertical shift downward of 1. Inside the parentheses, I see a plus 3, which indicates I would also expect to see a horizontal shift left 3 units. So I know all these things. I also have to make sure I apply them in the right way. Following order of operations, following correct order. What they would have you do is do each one of those individually, and then graph each one individually. So you have a bunch of graphs, and then you have to emphasize your final one. A lot of students, when they try to do it that way, get confused about where they left off, and they end up moving the wrong graph again, and it gets to be confusing. And plus, they're really not keeping track of the coordinates as accurately as they should, which is why I use this technique that I'm about to show you. I want to define for this a new X and Y chart. It's going to have 5 ordered pairs in it that make up the key points of this graph that I'm going to be able to use to redraw this. And I should also end up with something that looks a lot like the original. So when I look at this, I'm looking for, okay, what's going to happen to my X's? What's going to happen to my Y's? Well, X's are affected by horizontal transformations, and I only have one of those. That occurs inside the parenthesis. I see a plus 3 in there. Now, knowing those rules we kind of reviewed before this, I know that adding 3 inside a parenthesis means that I should be subtracting 3 from my X's. So when I go up to my original parent function, each one of those X values are going to be subtracted by 3. There's no other horizontal transformations in here, so I'm safe writing it now. So negative 13, negative 7, negative 1, 3, and 5. So those are going to be my new X coordinates. The Y coordinates are occurring with things outside of parentheses. I see a multiplication of negative 2. I see a subtraction of 1. That's what's going to happen to my Y coordinates. It's going to happen in that order because that's the order of operations which I obey outside the parentheses. So my Y's, so the Y's, each one of them are going to get multiplied by 2 and then subtracted by 1. So 0 times negative 2 is 0, minus 1 is negative 1. Negative 5 times negative 2 is 10, minus 1 is 9. 1 times negative 2 is negative 2, minus 1 is negative 3. 5 times negative 2 is negative 10, minus 1 is a negative 11. And negative 2 times 4 is negative 8, minus 1 is negative 9. So now I have my new coordinates. Now again, the first 3 are the straight part. So when I start connecting dots, I want to connect them with straight lines. The last 2 are the rounded part, or the last 3 together are the rounded part. Also helps me with the drawing process. So now I'm going to go and use this information to graph my line, do my new graph. So first I'm going to plot my points. And of course the first 3 I'm going to do with the straight. And then the last 3, starting with the third one going to the fifth, the fourth and fifth, I'm going to do more rounded. And so that's what the graph would look like with these transformations. Notice that it looks very similar to the original. It's been shifted, it's been reflected, it's been stretched. However, it's the same shape. It's definitely related to this graph. If I get something that's totally different in shape, it's not related anymore. So you have to be careful when you're doing your plotting that you're plotting things in the right area. If it doesn't look the same shape overall as what this looked like, then check your plots, make sure your calculations are correct. That's one way of knowing that you're incorrect. For this one here, for B, I'm still going back to the original parent function. I'm not starting with this one because these two, there's a lot of different things going on. So I'm not going to be able just to say, okay, well, these are just related to each other. They're both related to this guy, but to transform this into this would be much more complicated. So I'm going to go back to the original parent. And when I look at the stuff I have to do for this one, now, again, I'm going to define what I need to do to my x's and what I need to do to my y's. The y's are easy. I have the only thing occurring outside the parenthesis besides the f, which is what defines the function, is a subtraction of 4. That's the only vertical transformation. And therefore, it's telling me to take my y coordinates and subtract 4. So if I start making a table, and I subtract 4 from all the y coordinates in the parent, I'm going to have -4, -9, -3, 1, and 0. Now, everything else occurs inside the parentheses, which means it is a horizontal transformation. I see I have a multiplication of 2, and I have a subtraction of 3. Now, I could define it using this and saying, well, the subtraction of 3 means I'm shifting right 3 units. The multiplication of 2 means I'm vertically shrinking by a factor of 2, which means I'm cutting things in half. However, I have to make sure I'm performing those in the right order. And that right order is according to the reversal of the order of operations. So basically, I'm not going to do the operations I'm showing. I'm going to do the opposite, but I'm also going to go opposite according to the order of operations. So the first thing I would do for the x's is I'm going to add 3. And then after doing that, I'm going to divide by 2. So when I look at this, I'm going to go to -10. I'm going to add 3. That gives me -7. Divide by 2 is going to give me a -3.5. I can write it as -7/2 as I want to as well. -4, I'm going to add 3. I'm going to get -1. Divided by 2, I'm going to get a -1/2 or a -0.5. For 2, I'm going to add 3. I get 5. Divided by 2, I'm going to get 2.5. And again, this is the straight part. The 6, I'm going to add 3 and get 9. Divide by 2, I'm going to get 4.5. And the 8, I'm going to add 3 and get 11. Divide by 2, I'm going to get 5.5. And again, this part's the rounded part. So now with my new table, defined off of the operations I defined I needed to do, I'm going to plot these points and draw the figure. There's my graph. And again, it should look like the original graph. Now here, there was no reflection. It got shifted around a bit. It got horizontally shrunken. But generally, that's what it looks like now. And that's how you would do graph transformations. They basically allow you to, focus on the main function where all the interesting stuff would go on, because that's what determines certain curves and things like that. Those various functions like square roots, squares, cubes, logarithms eventually. And then I just use all the additions, subtractions, multiplications, and divisions to move them and stretch them and shrink them into the right places that show like what the overall effect is of the graph. And that is the end of this video. If you have any additional questions, please make sure to ask about them in class or come to my office hours. Until I see you either in one of those two places or until the next video, have a good day and I'll see you around.